Okay, in this section, we're going to go over unit cells and specifically how to tell how much of an atom is inside the unit cell. So we'll compare in this little table two-dimensional square unit cell versus a three-dimensional cubic unit cell, which is actually what would be present in any kind of natural material like a metal. So in the problems where you have to find the density of something like a metal, you're going to be obviously looking at three-dimensional cells, but some problems may have you look at just hypothetical two-dimensional lattices. Okay, so there will be four general types of positions in terms of where the atom can be. We'll start with the corner position. So that would be an atom centered at the corner. And if it's two-dimensional, then the amount inside would be 1/4 of the atom. So if we have a three-dimensional unit cell, kind of the pattern that we'll see is that you basically just cut the 2D number in half. So now only 1/8 of that atom is actually inside this cube versus 1/4 of the circle here. So we have corner. Second would be edge. So centered on the edge, you can see that half of that circle is inside, whereas if you had an atom and you had a three-dimensional cell, 1/4 of it would be inside. Then we have what we call the face. So an atom right on the face of a two-dimensional would just be right inside the square. All of it would be inside, or the fraction could be represented as just a 1. And again, here, if we imagine there's an atom on the face of this cube, half of it's inside, half of it's sticking outside. So we're going to get half inside. And then we have body. This is not applicable because of the two-dimensional nature of this. You can't really have something inside of it three-dimensionally, where we can have that in a three-dimensional cell. So this would be kind of this space in the middle, and then obviously that would be completely inside. So we're going to have, again, a fraction of 1. So this will be important. Basically what we can do with this is determine formulas of, let's say, like ionic compounds. So we'll do one of those in these problems. Or let's say we can do like a density calculation of a metal. So those are generally the two applications of this. And we'll look at a couple problems to illustrate how to do that. Okay, number 3, we have a two-dimensional lattice. This is a hypothetical ionic compound. We want to figure out the empirical formula. So first thing you want to do is find the unit cell. Generally, there will be just a square unit cell, which is just a repeating unit, smallest repeating unit. And oftentimes there's a couple ways to do this. I can show you 2 potential unit cells that would work. It doesn't matter which one you pick, as long as you pick one that's a true unit cell. So if you want, you can pause and try to do that. And what you should come up with is a square like this. And if you translate that in either direction, sideways or up and down, that would just repeat. So then inside the unit cell, this is two-dimensional. So we're going to use our numbers from the table above. And I guess also we need to know which circles represent which ions. So if you remember atomic radii, in this case, the metal, this is not always the case, but we'll assume this unless you're told otherwise. The small size ion is going to be the metal, that's the cation. They're smaller. And then the larger clear circle will be the anion. Their anions are larger in radius generally. So in this unit cell, we have, for the metal cations, we have 4 atoms at the corners. And if you remember, that means that 1/4 of them is inside. We also have 1 on the face of this unit cell, so that's going to add up to 2 total metal cations in here. And if we look at the anions, how many are inside here? Well, we have 4 kind of on the face of this unit cell, so they're all inside. That's going to give us 4. So then if we put this together, we have a formula M2A4. Because it's an ionic compound, this is always written as an empirical or lowest ratio formula, so Ma2. So what we would actually get from that is that most likely the metal, well, the metal would have a charge twice the anion, so probably the metal would be 2+ and the anion would be -1 or something along those lines. That's kind of another layer we could go into, but just need the formula for now. So I mentioned another unit cell. Another possible unit cell that works is something like this, kind of this diamond. So if you think about that, also translates in any direction. If you kind of move that in either direction, you get a repeating pattern. And this is good practice. If you want, you can try with this unit cell how many fractions of each ion are inside, and you should end up with the same formula. Okay, so we're going to do density calculation of silver. And silver is crystallizing in a cubic closest packed structure. So this is also abbreviated as CCP, which is the same thing as face-centered cubic. So for this, what's important is there's a chart at the end of my chapter 16 handout that has different cubic unit cells compared, and it gives you the number of atoms in each cell and the edge length in terms of the radius, so you can check that out. The important thing with these density problems is you're going to want to know how many atoms are in the cell. So for FCC or CCP, cubic closest packed, we have 4 silver atoms per cell. And also you'll want to know that the edge length is the radius times the square root of 8, radius of the atom. So this is important, again, remembering for face-centered cubic structures, 4 atoms, edge is this. Because basically the density is a ratio of the mass of the unit cell over the volume of the unit cell. So that's kind of where we can start. There's 2 general calculations. You want to get the mass of the cell and the volume. And the mass is determined by the number of atoms. So we can take 4 silver atoms, and in order to find the mass, we're going to use the molar mass, which means we need to convert this to moles. So we have Avogadro's number of atoms, and the molar mass of silver, which is 107.9 grams per mole. So that'll give us a mass in grams. And then the volume we want to be in cubic centimeters. So density almost always is calculated in these units. So units are important to keep in mind in these calculations. But they're all pretty much standard. So once you do one or two of them, you're not likely to like change to different units for different problems. So you kind of hopefully get the pattern. Okay, so we're gonna have the radius square root of 8 gives us the edge length. The volume is the edge length cubed because these are all gonna be cubes. So keep that in mind. And because we want this to be in centimeters before we cube it, well, we want that because it's easier. So we want to have the edge length in centimeters. So I'm going to just down here convert the radius to centimeters, and that's just converting from angstroms to centimeters. So in the problem, it says that the angstrom is 10 to the negative 10th meters. If you remember a centimeter, there's 100 centimeters in a meter. So basically, the radius is 1.44 times 10 to the negative 8 centimeters. Okay, so that's going to go right here. Multiply that by the square root of 8. That's going to be our edge, this thing cubed. So then just wrote down what each of these calculations comes out to. The mass of the unit cell, 10 to the negative 22 grams. Makes sense, it's only 4 atoms, so it's pretty small. Also, volume is pretty small. Ten to the negative 23rd. So dividing mass by the volume gives us 10.6 grams per cubic centimeter for the density of silver. Okay, in this problem, we're going to find the radius of a titanium atom from the density of the solid titanium substance. So we're kind of going backwards. This is body-centered cubic unit cell. That'll be important for a couple of reasons. And so we have the density, if we remember, density is mass over volume. And the mass, is basically determined by the number of atoms in the unit cell. The volume is determined from the edge length, which is related to the radius. So kind of going backwards, that's what we want to solve for. So let's first find the mass. In BCC, we have 2 atoms. We have 2 titanium atoms. And we have Avogadro's number, 1 mole over Avogadro's number. And titanium is 47.88 grams per mole. So we should get a very small mass, like usual, for only 2 atoms of something. 10 to the negative 22 grams, sounds right. Now, if we solve for the volume, we can take the mass and divide by the density. This is just, again, solving this equation for volume here. So we take that mass of the unit cell, divide by 4.5 grams per cubic centimeter, and we get that the volume of one unit cell would be 3.53 times 10 to the negative 23. This would be cubic centimeters, right? Our standard unit for volume of unit cells. And then if you remember, the edge, these are all cubes, the edge length cubed gives the volume. So the edge would be the volume cube rooted, or to the 1/3 power. We just take this number to the 1/3 exponent, and that gives us 3.28 times 10 to the negative 8 centimeters for our edge length, right? And we have then some formulas that we would have to recall, or at the end of this handout, I have a little summary table of the basic unit cells, like simple cubic, body-centered cubic, and face-centered cubic. And for BCC, we have, it'll say 2 atoms per cell, and that's what we use in the mass. And then it'll say the edge is 4r over the square root of 3. So you can use that little table, and therefore the radius would be the edge times the square root of 3 over 4. So we just take this number that we got for the edge times the square root of 3 over 4, and that's the radius of our atom in centimeters, right? So this is 1.42 times 10 to the negative 8, so it'd be centimeters. So then it's just a matter of converting that to whatever metric unit you want, and we're going to do what, picometers. So we have down here, say 1.42, and then we have 1 meter is 100 or 10 to the second centimeters, and then it says in the problem that 1 picometer is 10 to the negative 12 meters. So you can set up these ratios whatever you want. Another way would be to set up 10 to the 12th picometers for 1 meter, right? That's the same thing in the end. And this would give us 142 picometers for our radius. Okay, so it's definitely good to practice those going back and forth and get really familiar and comfortable with those calculations. And again, just kind of watch the units and make sure you're got those all nicely situated. All right, talk to you in the next video. Have a good one.